Okay. Alrighty then. We're going to talk about the wire tables. Fundamental to electrical work is the National Electrical Code tables. They're in the current version of the National Electrical Code. And our objectives are to determine conductor ampacity. In other words, the ability to flow a certain amount of current. Discuss the resistance of the wire, insulation characteristics, temperature correction factors, determine conductor resistance. And we're going to try and be able to select proper wire sizes for the conditions, but there are a lot of conditions we're going to talk about. List parallel conductor requirements and discuss the Megger. I wonder if the Megger company got a little advertising going on with the Delmar Publishing Company. Okay, tables and charts. Chapter 3 of the NEC provides general information about wiring methods and materials. The wire tables, every electrician in the whole world, I should say, knows that the wire table that is most commonly used is 31016. There's a page out of 31016 in your book, I believe. And 13 is a table that's before 31016, and it talks about the characteristics of the insulation. It talks about the 3 columns. Now, the 3 columns have to do with duration ability. In other words, if a 60-degree wire has a certain ampacity, a 75-degree wire will have a higher ampacity at the same 60-degree rating. Or a 90-degree wire will have a much higher ampacity rating for that same 60-degree column. So the 3 columns are 60, 75, and 90. And they have to do with ambient temperature areas or derating, which is one of the main things we want to talk about today. Okay, correction factors. We will almost never say correction factors. We will say we are going to do some derating. We're going to derate the ampacities of the conductors that are stated. High ambient air temperatures reduce the current carrying ability, and low ambient air temperatures increase conductor ability. Well, that's not really quite true. I don't know of any place where you can add ampacity because it's below 30 degrees all the time. Even in Alaska, it gets warm some days. Some of the things you need to realize is that these tables are based on the highest ambient temperature that the wires are going to see. For instance, if you put a conduit on a roof 4 inches above the roof, the temperature of that conduit is going to be astronomically higher than the ambient air around you because it's going to get heat from the sun, it's going to get heat reflected off the roof, and because of that, there are places where you have to actually run conduit on above a roof, and those wires have got to be way bigger than they would be if they were anywhere else. Okay, temperature correction factors. And we only derate, we don't add ampacity. So more than 3 current, that's the other thing, it's high temperature, and then more than 3 current carrying conductors in a conduit. In the code book, there's a section, 31015B2A, I guess it is, where it tells you that above 3 current carrying conductors that you must derate the ampacity of the wire. We don't really need to talk about that just yet, but since I want you to remember part of that table from now on, does that mean memorize it? Yes, that means memorize it. And it's only 2 stages that I want you to remember. The first stage is for free. 1, 2, 3 for free. 1, 2, 3 for free. You don't have to derate wires up to 3 current carrying conductors in a conduit, right? So that's for free. 4, 5, 6 is 80%. Okay, that's a little hard to remember until you go to the next step and you go 7, 8, 9, 70%. Okay, so if you remember the 7, 8, 9, you remember the other one is 10% higher. Okay, And I do want you to remember those because they'll be on a quiz and you won't be able to look it up in your code book because you don't use a code book for this class, right? And you won't be able to look it up in your book because you don't get to use your book on a quiz, right? So 1, 2, 3 for free, 4, 5, 6, 80%, 7, 8, 9, 70%. So that means that well, we'll talk about what that means later. All right. Let's see. 4 factors determine the resistance of a length of wire. The type of wire material. In other words, if it were made of aluminum, it's going to be more resistive than it would be if it were made of copper, or more resistive than it were made of silver. Why don't we make wires out of silver? It's a better conductor than copper. It's a little expensive, right? And some people think that gold is a better conductor. That's not true. Gold is not as good a conductor as silver. It's not even as good a conductor as copper. Why do people put gold-plated screws in certain instruments or certain terminations where they don't, why do they put it in certain places? Some places they have gold-plated screws. It's exactly correct, corrosion. The nice thing about gold is it's not maybe not as good a conductor as copper, but it never corrodes in any way. It doesn't corrode at all. Okay. The other thing is the cross-sectional area. Now, cross-sectional area is something you've looked at since you were in 6th or 7th grade probably. Remember pi r squared? That's the area is equal to pi, 3.14, times the radius squared. That's the cross-sectional area of a circle. Very important factor now. We're going to use that information, and I even have this little idea of my own that I call ballparking the size of the wire, the size of the conduit, because what if you don't have your code book with you, and you've got to order some wire and some conduit, and you know what size the wires are going to be, and you just happen to have a few little pieces of that kind of wire with you, they're on the job, and you know you've got to order the conduit to put these conductors in, and they're going to be a mixed group. They're not all the same size. Okay? Then you have to do pi r squared for the cross-sectional area of all the wires, add that cross-sectional area up, use no more than a certain percent. Oh, that was right. We're going to talk about that today. And then find out what area conduit you have to accommodate that, to accommodate the proper fill, conduit fill or wire wave fill or nipple fill, or let's see, what is the other thing? And whether it's a single conductor, 2 conductor, or 3 conductor. But we're going to talk about that today. And the length of the conductor, generally speaking, you now have no control over the length of the conductor because you've got to go from point A to point B, whether it's from Arizona to here or whatever it may be, you've got to have that length of wire, and there's not much you can do about shortening the wires. So that's something you usually have almost no control over. And the temperature of the conductors, that's a direct influence on how much current a conductor can carry. Okay. This is the I squared R rule. The temperature of any material increases its resistance. An increase in resistance will usually increase heat. More heat will create more resistance, and so on and so on. Okay. Materials have a positive coefficient of temperature. Well, yeah, okay. We're going to talk about that later too. And a few conductive materials have decreasing resistivity with rising temperature. A few materials have decreasing resistivity with rise of temperature. And the resistance increases with falling temperature. These materials have a negative coefficient of temperature. Carbon, silicon, germanium. Where do those things sound familiar from? Somebody say semiconductors. That's correct. Okay, and the resistivity material, and look at copper. Now, Mr. Herman believes that it's 10.4. Our Singer math book, if you're in the math class, also believes it's 10.8. And then there's that wild hair Mike Holt, who has various numbers depending on what year you talk to him about. If you talk to him about the past, he's got one number. If you talk to him now, for copper, he's got a number of like 21. And if you don't know, I was a code expert on one of his code panels a few years ago, and I couldn't understand where he was getting this 21 from. And I wasn't sure where Herman was getting 10.4 and where Singer and all those people were getting 10.8. And so I started figuring backwards. I found there's a formula in the code book. Did you know that? For finding the copper constant, or any constant actually. And there's this big formula, and it has a little bit of, well, a foreign math method. That's all I'm going to call it. And any formula that you have, you can kind of flip it around to find out what the variable is that you're looking at, right? So I flipped it around and I did a reverse calculation, and I found out, hey, 10.4, something is based on 20. That's the bottom number on the table, 20 degrees centigrade. Ah! Now, that doesn't make any sense, because at 20 degrees, between 20 degrees and 30 degrees centigrade, you have a positive correction factor, remember? Right? But at 30 degrees and down, or higher in temperature, you have a negative, a derating factor, right? So derating factor starts at 30 degrees. Guess what number you come up with if you plug in 30 degrees centigrade instead of 20? 10.8. 10.8. Now, Mike Holt, so I took his number and I flipped it around and go, what the hell is he talking about? And guess what it is? 60 degrees centigrade, that equipment terminal temperature, which makes absolutely no sense, because the tables are set up for 30 degrees ambient temperature, not 60 degree terminal temperature. And if you're confused by that, don't worry about it. It's just that Mike Holt, I don't think, realized that he had confused two ideas, but that's a whole different opera. So anyway, we're going to use, even though it says 10.4 here, I want you to write this down. Copper coefficient that we will always use will be 10.8. I believe Singer, Foster, and Bertrand did some research and realized that the table starts deration at 30 degrees centigrade, and reversed the calculation and said, oh, that should be 10.8, not 10.4. And I agree with them totally, even though they never said that out loud. Okay? So there we go. So we're going to be using 10.8, and I'm not even going to talk about aluminum, because all calculated, what does it say in the code book, by the way, about copper or aluminum? It says all calculations are copper unless stated otherwise. You know, when you do any kind of a course where it's code, all the questions, even the California State Inspector's License examination, says on the test, all questions refer to copper unless stated otherwise. We're going to do the same thing. Unless I state otherwise, assume copper. And by the way, I almost never will state otherwise. So you can safely calculate with copper and assume that you're doing the right thing, at least for this class. Okay. Now, wire tables and conductor size. A mil is 1/1000th of an inch. Now you have to realize that they came up with this crazy method of looking at cross-sectional area that really doesn't make sense, but we're kind of stuck with it. It was done back in the Brown and Stewart era, back when they were figuring out how to figure out the gauge of wire to begin with. A circular mill is a circle with a diameter of 1/1000th of an inch. Okay? So if something has, you've heard of wire that has 300 kc mills, that's 300,000 circular mills. So if you look at this formula, what does that mean? It has a diameter of 300,000 circular mills. Has a diameter of 300,000 mills. So you can kind of see that that's kind of an American-centric wire gauge, but that's okay because it came from Brown and Sharp a long time ago. Diameter of wire is converted into mils. The number of mils is squared. Circular mils is diameter squared. Yeah, okay. That doesn't make sense, does it? Because that's really a square measurement. That's turning the circle into a square, isn't it? It's actually, well, we won't get into that because wires are measured in circular mils and we're kind of stuck with that. Okay. This is a quiz question someplace, someday. What is a mil foot? Okay, take a look at the picture, and now you know what a mil foot is. It's 1 mil in diameter, and it's 1 foot long. So now you know what a mil foot is, right? We'll talk about why you need to know what a mil foot is when we get there a little later in the book. Okay, when we're computing resistance, R is K, the copper constant, times the length, divided by the circular mil. R is resistance of the wire, and there's a chart in the code book that will tell you the actual ohms per foot for that kind of wire. Ohms per mil foot, copper, they say is 10.4. We're going to convert this to 10.8. Thank you. Very good. Length of the wire in feet. Once again, an American-centric formula. And circular mil area of wire. And we're going to have one more formula from that. Wire tables. Okay, let's go back. I'm going to introduce you to a new formula. I think the book is going to come to that anyway, but if it doesn't, I want to make sure that I give you this formula. Nice and final. Okay, we have K times L over circular mil, right? And what does that give you? Is that the resistance? Yeah, that's the resistance. But I'm going to give you a new formula. And I think it's later in this chapter, but I want to get it in now. And the formula is okay. 2 kil over circular mil gives you VD. Say it with me. 2 kil over circular mil gives you VD. That was terrible. Okay. We're going to say it again. I won't bore you with this on the recording, so I'm going to pause here for a second. Don't forget to remind me to turn this back on. Okay, now that we have the formula 2 kil over circular mil memorized forever and ever, because we said it a couple times, I want you to realize that this is for single phase only. This is for single phase. That means the 2 is there because the wire goes out to the load and turns around, and whatever's left over comes back. So you have 2 wires, one going, one coming back. Now what if I wanted to, now this is not the formula we use if we're trying to find the size of the wire to actually use because of the voltage drop, right? What we're going to use is, now you know that anytime you have A over B is equal to C, you can reverse B and C's location. So we're going to reverse this with this, and we're going to wind up with 2 kil over the voltage drop that you want to allow is equal to the circular mil. In other words, the wire, if you're looking for the wire size that you're going to use and you want to allow no more than a certain amount, then you use 2 kil over the voltage drop you're going to allow in the number of volts. The VD is the number of volts you're going to allow to be dropped. Okay? Now, we'll do some examples with this later. But now I want to talk about one more thing, and that's 3-phase. 3-phase is slightly different, and you would remember square root of 3 replaces the 2, and from there on it's the same. Kil over circular mil gives us VD. And then if we're trying to find the right size wire to use, we would use that same formula more or less. Square root of 3 over KIL times that over the voltage drop we're going to allow will give us the circular mil area of the wire that we're going to need to do that particular job. Okay, so we've talked about, we have 2 kil over circular mil gives you VD, and we can convert that to 2 kil over the actual number of volts we want to allow for a drop, and that will give us this actual wire that we want to use. Now that's a much more useful formula, because that's going to give us the wire size that will limit the voltage drop to what we want to limit it to. Now, why do we want to limit voltage drop? Because if you run a motor 10% low, it will cut its life in half. And the same is true mostly of any kind of equipment like that. Now, there's a rule, but it's not a rule in the code book. It's what's called a fine print note or an advisory, whatever you want to call it. It's not necessarily a part of the code. And it says basically that, and it's kind of a confusing fine print note. It says, don't allow voltage drop to be more than 2% to a certain load, or 3% from something, and it's hard to understand, but they mean from a sub panel, and no more than 5% ever. Now, what that really means is that they don't want to allow any more than 5%, right? Now, you're not always coming from the main service. Almost never are you coming from the main service. You're generally speaking coming from a sub panel, which is fed by a main service, right? Like in this building, we have a main service maybe in the first floor, or maybe in a completely different building. And all the sub panels, like the one for this floor, serve the loads in this area. Now, what this 2, 3, and 5 mean are that you can assume that you've lost 2% going from the main service to any sub panel, and that you should assume you've already lost. If you're going to a sub panel, you may assume that you've already lost 2%. So that means that since there's a 5% total, you should never allow any load going out from that sub panel to have more than 3% voltage drop. Okay, and that is generally the voltage drop that we'll work with, is the 3%. Because if it's coming from a sub panel, most loads come from a sub panel, that we need to allow no more than 3% voltage drop. Okay, that's a number that's going to keep coming up, 3%. Now, what about the 5%? If I'm coming from a main service, if the main service just happens to be sitting next door and we have a panel in it, and we're getting circuit breakers out of there and we're taking loads directly from that, we can allow 5% voltage drop, because that's the main service to us. We can assume that that's the voltage we have, and we can allow a 5% voltage drop. You need to remember those two numbers, 3% and 5%. If I give you a voltage drop formula and I say that it's coming from a sub panel, assume that means 3% maximum voltage drop. What is 3% of 120 volts? 3.6 volts is exactly correct. So anytime, now that number is going to keep coming up again and again, 3.6 volts. 120 volts is a very common service load voltage, and 3% is a very common voltage drop, so that number will keep coming up again and again. What's 5% of 120 volts? 6 volts even. Alrighty then. So those numbers will come up again and again. Trust me on this. So, but the part you need to remember is 3%, 5%. If something's coming from a main service, you can allow 5%. If it's coming from a sub panel, don't allow more than 3%. Have we messed up this slide enough yet? No, we haven't. Yes, ma'am. Okay, now let's look at our, as I said, we haven't messed up our slide enough yet, because we've got square root of 3 times K over circular mil. And that's for a 3-phase circuit. And what that means is that when you have the load balanced across 3 phase, you don't have a wire going out and a wire coming back. The load is balanced between the 3 loads, and because of that, the multiplier we're going to use is the square root of 3. Okay? And that's for all 3-phase loads. Any 3-phase load, you're going to use square root of 3 instead of 2. So you need to remember 2 kil over circular mil is the basic formula, and then we need to transform it either for 3-phase or you transform it to use for finding wire size instead of the voltage drop. And we're going to use both, because what we'll do is we will say that we have a certain thing at a certain place, and how big a wire do we need to have For instance, if we had a light and a little motor on a 120 volt circuit, a little light and a little motor, and it was 20 feet away on a number 14, a number 14 will serve that load no problem. But if we go out to the street corner of this campus and we want to put that same light with a little motor to turn the sign and shine a light on the sign so we can have a turning LA Trade Tech sign, then it's going to be on a much longer pair of wires, right? And how big a wire do we have to have if we do that? Well, we can use that formula right here, 2 kil over the voltage drop that we want to allow, and since it's coming from a sub panel, we only want to allow 3% voltage drop, 3.6 volts drop between here and my little light, my little motor, right? But if we're going out, let's say 300 feet, how big a wire does it have to be now? Well, let's plug some numbers in here. Let me go to the next slide. Wire tables and conductor size. Yeah, we know all that. And I'm glad we have a little space on this slide because we're going to mess it up pretty good. And we have 2 kil over circular mil gives me VD. That's what I say to remember the formula. But we want to exchange these two again because we want to find the wire size we want to use to get our proper wire size without doing something else first. So it's 2 times 10.8 times current. Now we know that the little light and the little motor are going to draw, let's say 10 amps, which is way less than a number 14 can allow. 10 amps, that's going to be our whole load, but we're going out 300 feet. Now, we could divide by the cross-sectional area in circular mil for a number 14 wire, which is, give me the 411 on that, that's 4,110, or actually it's 4,009, I think, 109. The 411. But we don't, that will tell us how much voltage drop we would have if we run 14 out there. Now I think we're going to have more than 3.6 volts. Let's multiply that out. 2 times 10.8 times 10 times 300 is equal to, and then divide that by 4110. What do we get? So if we do this, we'll find that we lose 15.6 volts or thereabouts, right? Is that above 3.6? No, that's about 5 times above 3.6, right? Or 4 times, something like that. Way more than we want to allow. So let's do this in a different way. And let's put in, but I just took that out. Let's put in, oh, I took the whole thing out. Okay, we have 2 times 10.8 times 10 times 300, right? And we want to allow no more than 3.6 volts, right? Okay, so if we multiply that out, 2 times 10.8 times 10 times 300 divided by 3.6, that's going to give us a fairly large number. Okay, now, if we do this, we wind up with 18,000 circular mils. 18,000 circular mils. Now, what does that mean? That means that if you look up in the wire table, you'll find a wire that has a larger cross-sectional area than 18,000 circular mils, and that's the wire you're going to need to use. And by the way, that's about a number 4, I think. Off the top of my head, I'm not positive, but that sounds like a number 4, which is about 3 times bigger than a number 14 in cross-sectional area. The Brown and Sharp method, way back when in the dark ages, when they're finding the American wire gauge or creating the American wire gauge table, they were doing it for their own machine tool purposes. But what they did is every time they went up 3 sizes, they doubled the cross-sectional area. So you know that what they did here is, since we went up about 6 times, I think, we doubled the cross-sectional area. Okay. Let's see. What is our next slide? Wire tables and conductor size, computing single phase voltage drop. Okay, voltage drop is 2 times K times I times L. 2 kil over circular mill. Wow, look at that, ED. Okay. This is one time I use VD, by the way, and you know why? Because it sticks in your mind when we say 2 kil over circular mill gives you VD. It's just something to help you remember that we're talking about voltage drop. Okay, so there's my formula, the 2 kil formula. And let's see, and then here we have square root of 3 is substituted in for the 2 when we're doing 3-phase. And here we have the wire table conductor sizes. Parallel conductor rules. Now, there are a lot of rules about running in parallel. They've got to be the exact same, let's just say everything, okay? Same conductor material, same conductors, same circular mill area, same insulation type, same terminations of conductors, and same each, let's see what this says down here. Raceway contains all phase legs. In other words, you could run a parallel set in 2 different conductor sets, but you have to have, let's say it's 3-phase, you'd have to have A, B, C in one conduit and A, B, C in another conduit. And somehow those 2 conduits had better be the exact same length. And they've got to be terminated in the exact same kind of termination, material termination. Everything's got to be almost identical. And why is that? Because if one, it's like when you pick up, 6 of you get together and pick up a giant tree that's been cut down, a big log, and 6 of you pick it up. If somebody has got to pick up more load than everybody else, that one person may be injured because of the excessive load, right? Same is true with wires. Okay, if one is taking all the load, it may overheat and burn up. We don't want that. We want them all to run nice and cool, and running parallel is really neat. They left out a rule. You can't parallel all conductors. Let's see if they've included, I don't think they did. No, they didn't. You cannot parallel wires smaller than 1/0. In other words, it's only for big wire. Only for big wire. Unless it is for a special purpose, and we're not going to get into that. Just remember that generally speaking, you can't do that for little wires unless there's a special purpose, which we're not going to talk about right now. Okay, wire table and conductor sizes, parallel conductors. Okay. Installations are often checked with a megger before a system is energized. Why do they check it with a megger? To see that it has the exact same resistance from end to end. Okay? In order to test the quality of the installation, okay, we won't get into that. Wiring defects can be detected and connected safely. Okay, well, we won't get into that either, but a megger is okay for that, but if I want to know about leaks, I'm going to use a high pot, not a megger. Tested for shorts. You can do that with a megger. It's not going to show you all shorts at high voltage, though. So it's only going to show you certain kinds of leaks. Okay, wire tables and conductor sizes. Okay, there is so much we haven't done here yet. Okay. I told you we're going to do some derating. I think we're going to go through the next chapter before we do the actual derating calculations. So we'll do that after we look at the next chapter. So let me end this one, even though I went way over my 15 minutes. Let me stop this here, and we'll take a quickie break, if that's okay with you guys.